Most of the stuff I'm going to present today is going to be in regular jump. When we get towards the end, when we start to talk about the reliability of systems, I'll point out a couple of things that are available for Jump Pro users to be able to simulate those kinds of systems. But where I really want to start is what makes repairable system reliability different. Because one of the challenges that I've had over the years is to try to understand how you explain for both repairable and non-repairable systems, you're dealing with Weibull distribution, or one of the more common distributions that gets used is the Weibull distribution. Now, what's the difference? The underlying distribution in both cases is Weibull. Let's say I'm doing a Weibull analysis, and I'm modeling my data using the Weibull distribution. So the underlying distribution is Weibull, but it's the differences between repairable and non-repairable systems are subtle, but very subtle and but important, and fortunately on the surface fairly simple. So the big difference is that when I'm dealing with a non-repairable system, I only get to see one failure. Once the system fails, or once the object fails, it's broken. I don't observe any more values from it. So the observations that I'm looking at when I'm dealing with the Weibull distribution, they're going to be independent and identically distributed. Whereas when I'm dealing with entities that are repairable, the failure that I see might not be the first failure, it might be the second or fourth or 10th failure. And that makes a difference. In that respect, when we're dealing with failures from a repairable system standpoint, those failures are dependent. They're dependent on when the last failure occurred. And you need to keep that in mind when you're modeling this data, because if you take repairable system data and you try to use something like life distribution, you're going to get the wrong parameter estimates. The right distribution, but the wrong approach, the wrong assumptions when you're fitting that kind of model. So one more thing I want to point out is that in doing this for many years, folks a lot of times will say, well, I'm going to be dealing with the Weibull distribution. My beta equals to 1 means that my failure times are independent, that the time to the next failure is independent. And that is true, but that's only true in the case of repairable systems. So I've put together a little simulated data set here. I've simulated 500 observations, and I'm looking at 500 observations in 4 different cases. In the first two columns that we're looking at 2 different Weibull distributions. The first one has a Weibull, it's got a beta of 1 and an alpha of 1,000. Second one's beta of 2 and an alpha of 1,000. And the other 2 cases that we're looking at, the last 2 columns, we're dealing with repairable systems. So these failures occur according to a repairable system. And again, same parameter estimates. The Weibull with beta 1, alpha is 1,000, Weibull beta 2, alpha 1,000. Now, if I were to generate observations from those distributions and then just use the distribution platform, this is what they would look like. So here's my beta of 1 for my non-repairable systems. Does not look flat, does not look like the distributions are uniform, which is what you would expect when you have this memoryless process, when my arrival times are occurring independently. Same thing with the Weibull distribution of 2. So that's the distribution of my failure times. The only place where you do see a uniform distribution of these failure times is the repairable system, but when the beta is equal to 1. Doesn't matter what the alpha is, as long as that beta is equal to 1, I'm going to get this memoryless process. Think of it, a lot of times folks will talk about the bathtub curve. So this is the flat portion of the bathtub curve when we're dealing with failures that occur in that time. Let me move on to some of the jump platforms that we're going to be dealing with. There are 3 platforms that I'm going to focus on predominantly. 2 of them are for repairable components. And these are going to be in regular jump. One is recurrence analysis. Okay, that's probably one of the older reliability platforms within jump. The other is reliability growth. And they do sort of the same thing. However, there's a couple of different features in each of them. And I'm going to point out what those are. The third platform that we're going to talk about is when we have systems of repairable components. So here I'm not dealing with a single component that I'm looking at over the course of time. I'm looking at actually a system, let's say a manufacturing floor, or maybe an automobile, or a computer. So in this case, I'm dealing with components that may or may not be repairable. In many cases, we're dealing with these components within the system that are in fact repairable or maintainable. I mean, how do you model that? Okay, so those are the three platforms we're going to look at. We're going to look at recurrence analysis, we're going to look at reliability growth, and we're going to also look at repairable system simulation. Now, I might have to make a quick side jog because many of you have Jump Pro. You're probably wondering, well, what's the reliability block diagram platform? And the reliability block diagram platform is kind of an intermediary. It's dealing with systems, but systems of non-repairable components, or at least components that I'm not considering being repaired. Okay, and I'll show you kind of the relationship between RBD and RSS just to make things a little bit clearer. All right, so let's start with repairable components. Let's start with recurrence analysis. I'm going to be drawing a lot of examples from a great book that came out it's probably 20, 25 years old now. And by the way, I know I'm not gonna have enough time to cover absolutely everything. A couple of places to look in the journal. That very first link, one of my colleagues, Don Michelson, came up with these deeper dives. So if you click on that link, it brings you to these deeper dives in repairable system reliability. There are a series of 6 videos. She goes into a little bit more detail, not only in the theoretical aspects, but also how do you apply these in Jump. So that's a great resource. If you want to dive a little bit more deeply in terms of having a text, say, and many of the examples that I am going to be talking about today come from this book. This book was put out about 20 years ago. It's by Wayne Nelson. Wayne Nelson is, I believe, he's an an ASQ fellow. He worked at General Electric for a number of years. Worked a lot in terms of modeling recurrence analysis. So this is a good book. If you don't have, if you're looking for something that's a little bit more applied, that doesn't necessarily go as deeply mathematically, this is a good place to start. Okay, so this is a good book. I was fortunate enough to take a short course that Wayne gave at the Quality and Productivity Research Conference back 20 years ago. And this is where these examples actually come from. Actually, I believe they're in his book as well. If you want something a little bit deeper from a mathematical standpoint, this is the book to look to. This is what I keep on my bookshelf. It's Cook and Lawless. The mathematics at times get a little bit deep. I've been probably reading on this for 10 or 15 years, and there's still parts that are just a little bit too deep for my understanding. And I'm an applied statistician, but it's very, very thorough, good reference to know about. So if you want to learn more, those are some references that you can take a look at. All right, so first example that we're going to look at, we're going to talk about automatic transmissions. So in this case, what we have is a number of different vehicles. Let's see, I've got 34 different vehicles, and these are indicated by the ID. The mileage indicators in this middle column is either when repairs occurred, or a breakdown occurred, or some changes to the system occurred, or when it was taken out of service. So you'll notice that anytime there was a repair that occurred, I'm going to indicate 1 as a repair occurring. When it was taken out of service, when the observation stopped occurring, I'm going to put a 0 there. So this, if you're familiar with using the censoring column in some of the other reliability platforms, this is just the opposite. Typically in censoring, it's 0 when it's not censored, and 1 when it stops. Just a complete opposite with repairable systems. All right, so pretty simple how to model this. It's going to be under the reliability and survival. It's going to be under recurrence analysis, and you need an ID. So even if you only have a single ID, so you can model this with just one item, but you still need to have that column in there. Just create a column with a constant value. That would work. Definitely need my time to event. Now, if we look down here at the cost column says optional numeric. Read through the documentation. You really need that cost column in there. You need to indicate at least when that particular item went out of service. All right. So in most cases, I mean, I could not come up with a case where you wouldn't use a cost column. So you need to put a cost column in there, even though it says optional. All right, now some standard graphics. Again, if you go to Wayne Nelson's book, he has a whole bunch of these event plots in the book. If you're not familiar with an event plot, what it basically gives you is it gives you a line indicating the time something was in service, and then there's a dot anytime there was a repair that was made. Okay, so that's one very commonly used plot. The MCF, the mean cumulative function plot, is another plot that's commonly used in repairable system reliability, and that's just counting the mean number of repairs that occurred as a function of the usage variable. In this case, it's mileage. Now, the kind of the business end, the important aspect, the modeling part of repairable system reliability, in particular with recurrence analysis, is you're going to find that under the hotspot, and you're going to go down to fit model. Now, what I'm going to do now is I'm going to fit my model to my data. The default model is this power non-homogeneous Poisson process. So PHPP. This is my Weibull. This is my Weibull distribution. So if you go to the literature, if you work out the mathematics, the underlying distribution for a power non-homogeneous Poisson process is a Weibull distribution. So what this is saying is that the failures occur according to a Weibull distribution, and I am also taking into consideration the subsequent failures. Now, if I had some other extraneous variables in there, and we're going to come up with an example soon, I could say that I want to model my parameters, my alpha and beta parameters of my Weibull distribution differently for my input parameters. In this case, I don't have any input parameters, so this is analogous to what I would do for life distribution. So I'm just going to leave these blank. I'm going to run the model, and it gives me different names for the parameters. These are my alpha and beta parameters. So what this is telling me is that my beta parameter is 0.3. So that means if you were to go to the documentation, 0.3 beta parameter is where my reliability is increasing as a function of time, or I'm improving. And then the theta parameter is associated. It's identical to the alpha parameter. Now that's great, but really, what I like to see is I like to take a look at the profiler. And it's going to give me not only my hazard function or my instantaneous my intensity function, but it's also going to give me the cumulative number of failures. So, for example, I might want to know after let's say 25,000 miles, what is the cumulative number of estimated repairs that need to be made? So let me go ahead and put that in there. I'm just going to type in okay, 25,000. And that's going to tell me that even after 25,000 hours, given the data that I'm looking at, I only have about a third of a repair. So less than one repair. If I want to say, well, what is this is nice. I want some confidence intervals. I want to know at about what mileage I would expect there to be my first repair. And give me confidence intervals on that as well. So if I go under the hotspot to the left of my fitted model, there's an option to specify a time for my cumulative number of failures. And by default, it's going to put 1 in there. So this says that I would expect to see one failure at about 741,000 miles. And here are my upper and lower bound. My lower bound is about 362,000 miles, and my upper confidence interval is about 2.4 million miles. So it's pretty good. And if we look back at the data, we could see why that's the case. Most of the vehicles that we looked at, and let me go back to my event plot. Most of the vehicles we looked at had no failures whatsoever. I have one vehicle with one failure at about 20,000 miles. It really was that one vehicle that was a dud, right? We just had a whole bunch of failures. Other than that, everything seemed to work pretty well.